More than 4,500 years ago, the ancient Egyptians built the Great Pyramid, a monument that still dominates the landscape of Giza today. For decades, thousands of people took part in one of the greatest engineering achievements in human history. Standing 146 meters high, 2 million stone blocks and requiring over 20 years of work, its construction would have demanded a pace that, according to conventional estimates, was equivalent to placing a new block every few minutes. But what if lifting the blocks was never the real challenge? What if the real problem was maintaining a continuous workflow for decades? Perhaps the key to understanding how the pyramids were built is to look at the problem from a completely different perspective. For nearly 4,000 years, it remained the tallest structure ever built by human hands. Yet, more than 4,500 years later, we still do not know with certainty how such an extraordinary monument was built. When we think about the construction of the pyramids, we usually imagine enormous ramps along which massive stone blocks were hauled to higher levels. Most modern theories share one fundamental assumption: the blocks must have been raised by some kind of ramp. But if we examine these proposals more closely, an important question emerges. The entire construction process depends on a single route for moving the blocks upward. Over the years, countless solutions have been proposed to overcome this challenge. Lifting machines, lever systems, spiral ramps, internal ramps. Different ideas, yet all of them begin with the same question: how were the blocks lifted? But what if we've been looking in the wrong direction? What if the real challenge was never lifting the stones, but coordinating thousands of people over the course of decades? Perhaps the key to understanding how the pyramids were built is to look at the problem from a completely different perspective. The real mystery is not how the stone was quarried, nor how it was transported from the quarries, nor even how it was lifted to higher levels. The real challenge was keeping a construction project of this scale running efficiently, day after day, year after year, decade after decade. The most widely accepted explanation is based on the use of large ramps. As the pyramid rose higher, the blocks would have been hauled up long inclines to reach the upper levels. But this solution introduces an obvious problem. The entire construction process depends on a single route for moving materials up and down. And whenever an operation relies on a single route, a familiar phenomenon inevitably appears: the bottleneck. The higher the pyramid grows, the more difficult it becomes to reach the working areas, and maintaining a steady pace of construction becomes increasingly difficult. Yet the Great Pyramid was never the work of just a few teams operating in sequence. It was the achievement of thousands of people working simultaneously. And when thousands of people are working at the same time, organization becomes even more important than strength. Perhaps the real challenge was never moving a single stone. It was coordinating thousands of people working together over the course of decades. And if that was the real problem, then perhaps one enormous ramp was never the solution. Perhaps we have spent too long trying to discover how a single block reached the summit. But if the real challenge was avoiding bottlenecks, then the question itself changes. What if, instead of a single route, there were thousands of small routes leading upward? What if those routes were distributed throughout the entire structure? A single large ramp concentrates all the work in one place. A distributed system does exactly the opposite. It spreads the workload across the entire construction site. There is no longer a single point of access. There are no longer any bottlenecks. The construction site begins to function as a network. One ramp changes nothing. Neither do 10. But if the goal was to eliminate bottlenecks, then the solution may have been surprisingly simple. Repeat the same system thousands of times. Every new mini-ramp increases the construction site's capacity. Each new level creates new routes of ascent. Every mini-ramp becomes an independent working unit, built from remarkably simple elements. The stone block rests on wooden rollers. A main rope transmits the lifting force to the block. A lever multiplies the operator's effort, while a retaining post secures the load between each advance. The rollers dramatically reduce the effort required to move the load. But this advantage introduces a new challenge. The block can slide backward. Without a locking mechanism, gravity itself will pull the load back down the slope. To prevent this, a simple retaining system based on ropes and wooden posts is used. The rope is wrapped several times around a fixed post. With just a few turns, the friction generated is enough to prevent the load from slipping backward. This principle, known as the capstan effect, makes it possible to control heavy loads using an extremely simple system. While one rope pulls the block upward, the other ensures that every advance is securely held in place. Traction and retention work together simultaneously. Each movement advances the block only a few centimeters, but the process can be repeated again and again. What matters is not how far the block moves with each pull, but how many times the operation can be repeated. And when thousands of mini-ramps operate at the same time, construction no longer depends on a single route of ascent. The workload is distributed throughout the entire structure. Each mini-ramp can be operated by a small team of workers. A simple task, a short distance, an effort that remains fully under control. With thousands of teams working in parallel, a continuous workflow can be maintained throughout the entire project. The pyramid no longer functions as a centralized construction site. Instead, it operates as a distributed system. Our model begins with a remarkably simple idea. The pyramid does not grow by completing its outer surface from the very beginning. It grows from the inside out. As the structure rises, wide working platforms are preserved around its entire perimeter. These platforms provide space for transporting materials, organizing the workforce, and maintaining large, safe horizontal working areas. In our model, the pyramid does not grow by closing off each level as it is built. Instead, it expands from the inside out. Each new stage consists of adding a perimeter ring around the existing platform. As a result, the working surface never disappears. It simply moves outward, preserving broad horizontal platforms that allow construction to continue safely. The teams always work on wide, stable platforms, well away from the edge of the pyramid. Construction begins by expanding from the inside out. Each platform is built while leaving a wide perimeter ring around it, typically about 5 meters wide. This approach makes it possible to add successive levels while continuously maintaining large, stable, and safe working areas around the entire structure. Eventually, a point is reached where the pyramid can no longer continue to rise while maintaining a 5-meter wide perimeter ring around each platform. By then, the structure has reached a height of approximately 20 meters. This is an ideal stage for constructing some of the pyramid's internal structures. The Queen's Chamber, for example, can be built entirely in the open, with generous working space and none of the constraints imposed by an already completed pyramid. As construction continues, successive perimeter rings gradually enclose the chamber within the body of the pyramid. The pyramid now continues to grow by adding new perimeter rings, this time reducing their width to approximately 3 meters. In this way, the structure reaches a height of about 40 meters, creating another large working platform. At this stage, the King's Chamber can also be built entirely in the open. Once completed, the continued growth of the pyramid gradually encloses the chamber in its final position. Some of the temporary structures used during this phase would eventually become incorporated into the interior of the pyramid as construction progressed. The pyramid then continues to rise through the addition of new perimeter rings, now approximately 2 meters wide. Even so, each platform continues to provide a spacious and secure working area for the daily construction activities. By repeating this same process, the pyramid continues to grow steadily until it reaches a height of approximately 70 meters, while preserving a distributed construction system across multiple working platforms. A cross-sectional view reveals how the geometry of the structure itself naturally creates extensive working areas. Throughout the entire construction process, the teams can move and work safely without ever having to operate from narrow ledges. During the final stage, the height of each platform can be increased progressively until the monument reaches its full height. Finally, once it is no longer practical to raise heavy stone blocks to the summit, the pyramid ion could have been built using smaller, more manageable stones. In the end, the key may not have been the construction of one enormous ramp, but the transformation of the entire pyramid into a vast, distributed working platform. But one final transformation still remained. The outer casing was not installed while the pyramid was still growing. Instead, it marked the monument's final great transformation. In most modern reconstructions, the casing stones are placed as the pyramid rises, allowing the monument to gradually assume its final appearance. But this approach introduces a problem that is rarely discussed. If the casing is installed while the pyramid is still under construction, the workers must operate directly on a surface that is already supposed to be finished. Yet a smooth, polished surface with such a steep incline provides no practical platform for scaffolding or temporary working structures. As a result, temporary supports would have to be attached to areas of the casing that, in theory, should already have been completed. In our construction model, that difficulty simply disappears. The casing is installed only after the main structure has been completed. The wide step platforms remain available throughout the finishing process, allowing the work to progress from the top down without disturbing the sections that have already been completed. Each platform continues to serve its purpose until the very moment it is no longer needed. Only then is it absorbed into the core of the pyramid, leaving no visible trace of its existence as the casing work continues downward. Each platform is first filled with core masonry until it closely matches the pyramid's final slope. The casing stones are then positioned, carefully aligned, and finally polished. If this construction method was indeed employed, the ramps did not disappear. They simply became part of the pyramid's internal core. For centuries, we have searched for a single great ramp capable of explaining how the pyramids were built. But perhaps the real secret was never a single enormous ramp. Perhaps it lay in transforming one access route into thousands of small working fronts, capable of operating simultaneously, continuously, and independently. Thousands of mini-ramps working at the same time. A distributed system that made it possible to sustain the pace of construction for decades, before disappearing together with the monument itself. A construction model that not only explains how a pyramid could have been built, it also helps explain why the monument ultimately took the form we see today.